Hello everyone, I hope you're having a good break. So, as I promised, I'm going to solve the practice quiz 3. So, I'm going to go through the problems. I try to be as fast as I can, but I need some time to explain the problems and write the solutions. And as I mentioned during the class, I expect you to give me one file. Basically, email me one PDF file. So, because if you send me multiple photos, it would be difficult for me to look through the photos and then adjust the photos. So, if possible, just send me one PDF file. And if you have difficulties converting photos to PDF and just have like one united PDF file, just let me know on Monday or come to my office hour or just email me and I guide you how to do so. Okay, the first question is consider the following reaction. The equilibrium constant for the following reaction is, so equilibrium constant equals 4.9 multiplied by 10 to the power of minus 3. And the reaction is CO2 in gas phase plus H2 in gas phase. And as we talked about in the class, these two-way arrows mean reversible reaction. So not only reaction goes right to left, or rather left to right, it also, so CO2 plus H2 produces CO gas plus H2O gas, and CO gas plus H2O gas also produces CO2 plus H2. And to be more concise, we write half arrows. Okay, so to write equilibrium constant, what we do, we write concentration of one of the products, here H2O, to the power of the stoichiometric coefficient, which is 1, multiplied by concentration of the other product, which is CO, to the power of this coefficient 1, divided by concentration of CO2. Now in the denominator, we write the reactants. The power of 1 multiplied by concentration of H2 to the power of 1 equals. Now we just substitute what we are given. So now I'm basically solving part B. Or I can rather start with part A. So the question says, answer the following questions based on this reaction. Does this reaction proceed to the right or left? Explain. So do you remember that when we talked about this in the class, we said that we had two criteria for the reaction, go to the left to right or right to left. One of them was delta G of reaction, which is delta H minus T delta S, and we talked about enthalpy and entropy, and also K equilibrium, remember? And we said if, and we had like another definition, which was difference in Gibbs free energy in a standard condition equals delta H in a standard condition, or here we put like this standard minus delta S standard, and basically delta G 0 equals G minus G0. So this G0 means that Gibbs free energy at the standard conditions, basically at the standard pressure and standard temperature. And we're not solving problems regarding these specific standard conditions because I didn't want to go in too much detail into these concepts. But also delta H0 equals H minus H0, and most of books define standard conditions like room temperature and pressure of 1 atmosphere. And also delta S0 equals S minus S0. And we said delta G0, we had an equation that related delta G0 and equilibrium constant. Do you remember that? So delta G0 equals minus RT ln of K equilibrium. And you remember that ln is basically logarithm, and then the base is like Neperian number, and R is gas constant. And as you remember, R equals 8.314 joule per mole per Kelvin, and it can have like different units depending on what we're working on. And T is also temperature in Kelvin, as we have in the slides. Temperature in Kelvin. And these are all in lecture 22nd. And now I'm looking at the slides. It's like March 9th, 2022. So if you want to refer to the specific lecture, I'm just like repeating what I wrote for you before. In general, we had two criteria. If the difference in Gibbs free energy is negative, it means that the reaction occurs, or the reaction is spontaneous, or in other words, reaction, if we have like double arrow reactions, basically AA plus BB gives CC plus DD, and for this reaction, if delta G is negative, it means that this reaction occurs. Basically, reaction is left to right. And the equivalent to that was if K equilibrium is greater than 1. And also, if delta G is positive, it means that K equilibrium is less than 1. And I also showed you in the class mathematically that why these two sentences, or these two expressions rather, there are like this. Because if K equilibrium is greater than 1, you remember that this expression is positive, so delta G0 would be negative, right? And then the same thing here, if K equilibrium is less than 1, this would be negative, and then negative multiplied by negative would be positive. So going back to the problem that I asked you, does this reaction proceed to the right or left? Explain. So you only need to look at the equilibrium constant for 0.9 multiplied by 10 to the power of minus 3 is less than 1. So if equilibrium constant is less than 1, it means that delta G is greater than 0. It means that the equation goes, it doesn't want to go this way. It doesn't want to go left to right, right? So it goes right to left. And then for the second part, it says if, I already wrote the equilibrium constant expression. So here for B, it says, and we already have like equilibrium constant 4.9 multiplied by 10 to the power of minus 3. If 0.2 moles of CO2, and I just substitute in the things that I have, right? And the other thing that we should consider before I write this, these are concentration. So remember that when I see this denotes concentration. And concentration, one of the units is mole per liter. It can be gram per liter, it can be kilogram per liter, but one of them would be mole per liter. So if 0.2 moles of CO2, right, on all of them, we have like the volume as 4 liter, and I write mole here. And I'm just substituting in what I have here. 0.02 moles of H2 divided by 4 mole per liter. And for H2O, I want to calculate moles of H2O. So I just write moles of H2O, right? And finally, we have CO. 0.005 moles of CO divided by 4 liter. So you're welcome to divide everything, but one easier way to solve this is to simplify. These 4s and these liters, they cancel out. And the same thing with like the other units. You see that these moles can also, so this number, I just put here X as the number, but the units moles would cancel out, you see. So this is equivalent to 4.9 multiplied by 10 to the power of minus 3 equals 0.005 multiplied by X divided by 0.2 multiplied by 0.02. So you remember that when we want to find X, it would be the part that is known divided by a coefficient of unknown. So you can put that in calculator, or simply you can multiply numerator and denominator by 1000, right? So this guy cancels out. So would be 5. And then you can multiply numerator and denominator by 2. So it would be 4.9 multiplied by 0.4 multiplied by 0.02 divided by 10. And you can also, we can just write, maybe we can do this math in our head. If I'm doing this right, let's see if I can do this. 2 multiplied by 6 is 12. And now I'm gonna put this number in calculator to see if I did this correctly. Okay, it turned out that I did a mistake here. So when you do this multiplication, this is like 36, and then 4 multiplied by 4 is 16, and then when you add that, it would be 19, but I put like the other way around. So it would be basically 1.96 multiplied by 0.02. So 1, 2, 3, 4. 1, 2, 3, 4. Okay, so this would be 0.0392 divided by 10, which is like 0.00392 moles. Okay, that's why I always advise the students to, put the numbers in calculator and also calculate it yourself to compare, but never trust either of them, because you might make a mistake like I did. Anyway, so this is the first part of the, or like rather the first part and second part of the question. What is the unit of equilibrium constant for this reaction? You see, equilibrium constant equals concentration multiplied by concentration to the power of H2O, CO, H to the power of 1 divided by CO2 to the power of 1 multiplied by H2 to the power of 1. you see it was what, moles per liter multiplied by moles per liter divided by moles per liter multiplied by moles per liter. So this would be unitless because everything cancels out. You see these two and that two. I guess better way to say these two cancel out and then also these two cancel out. But in the exam, pay attention because depending on what coefficient you have here, if you have AA plus BB equilibrium with CC plus DD, depending on these coefficients, you can have different units. But for this problem, your answer would be unitless. So that was the first question. Now let's look at the second question. What is enthalpy, entropy, Gibbs free energy? When does the reaction proceed to the left? When does the reaction proceed to the right? Those two parts I covered in the last question, so just listen to that real quick. How can we relate Gibbs free energy and equilibrium constant? I also covered this part of this problem in the previous question. But for enthalpy, entropy, Gibbs free energy, again, I refer you to lecture 22. I'm trying to find the exact slide. Okay, lecture 22 on slide 2. We talked about enthalpy, entropy, Gibbs free energy. So basically, at constant pressure, reaction energy is called enthalpy of reaction. So it's heat of energy. And also entropy is associated with a state of disorder, randomness, or uncertainty. For instance, when you have if you have AA plus BB in equilibrium with CC plus DD, and for instance, if all of your matter are in gas phase, the side that has more moles, if C plus D is greater than A plus B, entropy increases. So in general, as long as you know the definition of entropy for this question, that is enough. And also Gibbs free energy is interplay between enthalpy and entropy. And these are related with this equation. And T here is absolute temperature in Kelvin. And as I mentioned before, if reaction, when does it proceed to the left to right, right to left, and also how can we relate equilibrium constant and Gibbs free energy, I explained in the previous question. Write the definition of an exothermic and endothermic reactions. Define transition state. Explain the difference between thermodynamics and kinetics. Okay, so endothermic and exothermic reaction, the answer to question 3 you can find in lecture 23. Let me check. Yes. And in exothermic reactions, basically heat is released, right? Or in other words, an exothermic reaction evolves heat energy. And delta H is less than 0, is negative. So this is a exothermic. And endothermic reaction, in endothermic reaction, system absorbs energy. Or in other words, delta H is positive for an endothermic reaction. Or in other words, an endothermic reaction takes in heat energy. And these are like slides 10 of lecture 23. When does the define transition state? You can see transition state in slide 14 and 15. slides 14 and 15. So as we said, transition state is a state that bonds of reactants are broken and they are in the process of forming bonds between reactants. In other words, at the very top of the energy barrier, so if you have like here energy and here this is your reaction coordinate, if you consider something like this, and this is like your activation energy, right? So at the top of energy barrier, the reaction is at its transition state, which is the point at which the bonds are in the process of breaking and forming. So here you will be having your transition state. Okay. Explain the difference between thermodynamics and kinetics. Dynamics and kinetics. I remember I had a professor that always was telling me that most of the time, 99% of the time, when someone asks you what is the difference between this and that, you just give the definitions. So thermodynamics tells us whether or not a reaction occurs. Or if you have AA plus BB gives CC plus DD, and also CC plus DD gives AA plus BB, you know, but with the help of thermodynamic, whether reaction goes right to left or left to right, whether a reaction occurs or not. It doesn't tell you anything about the speed of the reaction. But kinetics tells you the speed of the reaction. It doesn't predict whether or not the reaction occurs or not. It tells you the speed of the reaction. So this is basically the difference. And you can also read more about that or also watch the video that I have the link in slide 21 to have like the difference between thermodynamics and kinetics. And also I explained about, or your book rather, about reaction rates in slides 17, 16, 17. We have like kinetics and we also talked about thermodynamics. Okay, let's go to the next question. Write the definition. Okay, write the IUPAC name of these two compounds. So first, let's start with this one. Okay, when you want to write the name of the compound, first of all, when you have double bonds, remember that you should find the longest chain involving all the double bonds or multiple bonds. So for that matter, you cannot go like this, because if you go like this, one of the double bonds, this one, basically is not included. So remember to, if I can do this, okay. Remember to first choose the longest chain that involves all the double bonds and triple bonds, or multiple bonds, as your book says. After doing that, we want to name the carbons. So remember that we want to encounter the double bond or like the multiple bond, go from the direction that we encounter those first. So if I go this way or that way, both of them would be the first carbon. So if I say 1, 2, 3, 4, 5, 6, or if I say 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, 6. In that matter, they would be the same. So I just simply go here 1, 2, 3, 4, 5, 6. But the point is that if I go this direction, so if you could go in the sense of multiple bond, you could go either direction. We go from the direction that we encountered the branch sooner. If I go like this, the branch would be on carbon number 5, but if I go this way, let me also name it the other way. If I name it 1, 2, 3, 4, 5, 6, now I encountered the branch on the second carbon. So that's why I choose this one. I hope this is clear. So okay, there are several things to consider. First of all, you should write the carbon names, or like the number of carbon numbers that have the multiple bonds. So here we say 1, or I do that with blue, dark blue, 1, 3, 5. And you see each double bond has like 2 carbons on either side, right? We write the number of carbon that is lowest. For that matter, I write 1, 3, 5. I don't write 2, 4, 6, right? And we have 1, 2, 3, 4, 5, 6 carbons, so it would be hexa, right? So if this was, something like this, 1, 2, 3, 4, 5, 6, it would be hexene, right? But here, remember, you have 3 double bonds. Do you remember what we would call those? We would call those triene. It means that 3 of double bonds. Remember? And also, we have methyl, this is CH3, on carbon number 2. So it would be 2-methyl, 1, 2, 3 hexa triene. Okay, let's go to the next one. So we have something like this. If I can draw this good enough to demonstrate. Don't want to be perfect, just as long as I can demonstrate the point that I want to make. Okay, looks like some kind of bug or whatever. Anyway, so you see, we have like 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 carbons. And we have like a ring structure. Do you remember what we would call this? Cyclo, it should be decane if it was just like if it was all the bonds were single bonds, it would be decane, cyclodecane, right? But we have like double bond. If it was like only one double bond, it would be like decene, right? But we have 2 double bonds, so we say decadiene. Remember that this is 2, right? And we want to, we don't have any branches, but we want to say which carbons, they are attached to double bonds, right? So these carbons. So any direction, you just start from one of the double bonds. If you say here 1, you cannot go this direction. You should go somehow that you pass the double bond. Does that make sense? So that's why you should go necessarily this direction, 2, 3, 4, 5, 6. So it would be 1 and 6 cyclodecadiene. Just feel free to email me or ask me in the class, or just stop by my office if you have any questions about any of this. Next question. Name 5 unsaturated hydrocarbons that exist as cis-trans isomers. I also told you, for example, 3-hexene exists as cis-trans isomer. However, ethene does not exist as cis-trans isomers. Explain why these compounds exist as cis and trans isomers. What type of isomers these compounds are. Remember, when we talk about cis-trans isomers, and in general, when we talk about unsaturated hydrocarbons, we mean hydrocarbons that have multiple bonds, whether double bonds, triple bonds. And in this class, we talked about cis and trans isomers in two instances. One of them were when we talked about cycloalkanes, the other one was when we talked about alkenes. So here we should name alkenes that have cis and trans isomers. And this is in your lecture 21st, basically March 7, 2022, chapter 3. And I had a slide for you that I wrote based on the reference that I listed, that there are two requirements for cis and trans isomers. So first of all, rotation must be restricted in the molecule. So rotation must be restricted. And the second is that there must be two non-identical groups on each doubly bonded carbon atom. And you just answer the questions that I asked you. Since I'm recording the video and I want that to be educational, I'll explain more things and go through the lecture, review them, but you can just simply answer the questions. So don't feel obligated to write these things down. So one example that is listed in slide 4 is this structure. CH2, CH2, CH3. And also, if I write CH3, CH2, H, CH2, CH3, H. Can you name this compound? You can also pause the video and try to name the compound. Remember, when you want to name it, you should have the longest carbon chain involving the double bond, right? So, and when we count the number of carbons, 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, 2, 3, 4, 5, 6, and it would be hexene, right? Because you have double bond, you have 6 carbons, so it would be hexene. And in carbon number 3, you see that you have the double bond, and one of them is cis structure, basically this one, because the both CH3, CH2 are on one side, and then this one would be trans, right? So this is cis 3-hexene, this is trans 3-hexene. And I asked you to write 5 unsaturated hydrocarbons. You can write 5 different structures in a similar manner, meaning that, for instance, you can have carbon double bond, and then you can have, for instance, you can have, for instance, chlorine here, or you can chlorines on one side, and then here you can have, for instance, only hydrogen, right? Remember, the valence of carbon is 4. 1, 2, 3, 4. 1, 2, 3, 4, and here. So what about this structure? What do you think of that? This can also be cis and trans, right? Remember the thing that I just mentioned, that first of all, rotation must be restricted, in the molecule around the double bond. The other thing is that there must be two non-identical groups on each side of the double bond. It means that, or rather I should say on each doubly bonded carbon atoms. It means that for instance on this side we have like two non-identical groups, right? Cl hydrogen. So here we have like the trans, right? Because the two chlorine atoms on are different sides, and then here we have like the chlorines on one side, so it's cis. Can you write the name of this compound? So the longest chain is just like ethene basically, and then you have like 1 and 2 dichloroethene, and this is the cis. This is the trans. We can also write cis and trans before the name of the compound. So it says this is cis 1 and 2 dichloroethene, this is trans 1 and 2 dichloroethene, and the same for like cis 3-hexane or like trans 3-hexane. So the other structure, for instance, we can substitute chlorine with bromine, right? So if I just have like the same structure and then here I substitute this with Br, right? It can be another example. So it would be cis 1 and 2 dibromoethane, trans 1 and 2 dibromoethane. To write another structure, you can simply have carbon-carbon double bonds, and the same thing that you did before, we can put like 2 hydrogens on both sides. Here we can put, for instance, CH3, CH2, CH2. And then here again we put CH3, CH2, CH2. And so this would be cis structure. For trans, we put these on different sides, right? So we say CH3, CH2, CH2. Then here hydrogen, here hydrogen. Here it would be CH3, CH2, CH2. So what would be the name of this compound? Again, remember that we choose the chain that has the double bond in it, the longest chain, and excuse me, and we name the carbons so that 1, 2, or I guess that was technically right. Just remember that this would be, if you want to write the structure more thoroughly, remember that this, you have CH2, CH2, CH3, right? And the same thing the other side, CH2, CH2, CH3, right? So when you want to name them, you start from this carbon here, from CH3. 1, 2, 3, 4, 5, 6, 7, 8, right? So in other words, here 1, 2, 3, 4, 5, 6, 7, 8, and the number of carbons you see would be 1, 2, 3, 4. So this would be 4 octane, and this would be cis structure. This would be trans structure. Okay, so right now I wrote 1, 2, 3, 4, and any other compound that you write that they have cis and trans structures, as long as they have double bonds and they are unsaturated, it would be correct. So you can also write, for instance, if I write, what if I write CH3, CH2, 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 right? I add one CH2 here, right? And here, sorry, not here. And then here I also write CH3, CH2, CH2, CH2. What about this compound? I guess here I write okay, how can I write the name of this compound? Say 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 is decene 1, 2, 3, 4, 5 on carbon number 5, right? 5 decene. This would be cis because these CH3, CH2, CH2, CH2 are on one side of this carbon-carbon double bond. This would be trans because these are on two different sides. And now I hope you can write also cis and trans structures for any other compound or for any other example. But as I said, these are only some examples. You're welcome to write any other examples. Now let me look at the next question. Okay, and also says explain why these compounds exist as cis and trans isomers. What type of isomers these compounds are. As we said, these cis and trans isomers, they are not interconvertible by rotation around the double bond, and as a result they are configurational isomers. And also in lecture 20 we talked about, and section 3.5 in your textbook, we talked about cis trans isomerism in alkenes. And we said these stereoisomers are not readily interconverted by rotation around the double bond at room temperature. Like cis trans isomers of cycloalkanes, they are also configurational stereoisomers. Okay, so let's go to the next question, which is question 7. Explain the difference between question 6. Question 6. Which type of bonds are stronger? Sigma or pi? Explain when do sigma and pi bonds form. When sigma and pi bonds form. Explain the difference between sp2 and sp3 molecular orbitals. So the answer to all these questions can be found, first of all, in your book and also the 20th lecture. And specifically, if you look at slides 8 to, and almost always 2 slides, I have like one, the raw slide, the other one is the slide that I write in this Explain Everything software. So basically 2 slides are the same. So slides 8 and 9 are the same, 10 and 11 are the same, and also 12 and 13, and so on and so forth. But after slides 8 and 10 talk about, sigma and pi bonds. In nutshell, sigma bonds are stronger than pi bonds. And they are the strongest type of covalent chemical bonds. And sigma bonds are formed by head-on overlapping. Head-on overlapping between atomic orbitals. Meaning that if we have like p orbitals, and this is, excuse my sloppy drawing, p orbital plus s, right? You see that they form here ps sigma bond. And in other words, remember I said if you have like the axis for these two, they align. So this head-on overlap. Or the same thing if you have like sp3, right, molecular orbital plus s atomic orbital, it also gives you something like this, sp3s pi. Sigma bond, or like two p orbitals, if you mix them, this is not distorted, it's kind of like symmetrical. It would be something like this, right? Or sp3 molecular orbital plus sp3, right, becomes sp3 sigma bond. So it's head-on overlap between atomic orbitals or also molecular orbitals. On the other hand, pi bonds are again types of covalent bonds, but if you have like two pi bonds, for instance, like this, cannot draw this well, okay, something like this, drawing, okay, this and this, okay, kind of 1 pi plus the other pi, right? These give, if they mix, or if these two pi orbitals, and if you have the axis, you see that they're not, again, they're not like, they don't align, they don't have the same axis. So in other words, if you want to write it concisely, it would be the overlap of each two lobes. Or pi bonds are covalent chemical bonds, and in each of which two lobes of an orbital overlap with two lobes of an orbital. So you have something like this, and then in the slides we have like much better shape. What I do is that I will write these two guys here, this one and the other one. Doing a terrible job at doing this. And now these orbitals overlap kind of like this. like this. As long as you know, and here in the question I didn't ask you to draw them, so you don't have to super worry about them. You see, I even struggle having a nice picture. But for pi bonds, you know that 2 lobes of an orbital on one atom overlap with 2 lobes of an orbital on another atom. Or in other words, you can say this overlap occurs laterally. The overlap occurs laterally. Okay. Now, the difference between sp2 and sp3 molecular orbitals. And again, for these sp2, sp3, you can refer to slides 12. And I have like in slide 13 the review of the previous lecture, but if you go to lecture 19, let me tell you which slide exactly it was. In slide 19, or lecture 19, actually it's a slide 19 too. Slide 20, you can also see sp3 molecular orbitals. So for sp3, when you have the atomic orbitals, you have 2s and then 2p, and this is in the context of carbon, but can be for other energy levels, 3s, 4s, and so on and so forth as well. But in general, you have like 2 electrons in s orbital and then 2 electrons in p orbitals, and then these are like atomic orbitals, and here for carbon, and this is like energy. And then for the molecular orbitals, remember that we said these 2 electrons, one of them goes to this here, and then we'll be having like 1, 2, 3, 4 equal energy sp3, 4 equivalent sp3 hybrid orbitals, right? But when we want to have, going back to lecture 20, slide 12. We have, again, if we consider carbon, that has like 2s and 2p, right? This is energy, this is atomic orbitals of carbon. And now for sp2, we have, again, this electron, one of it goes here, but 4 of them don't have the same energy. One p orbital has like the same energy as like p orbital here, but we have 3 equal energy sp2, and then we have 2s and 2p orbitals are combined to form 3 hybrid sp2 orbitals, leaving 1 electron still in a p orbital. And this sp2 hybridization would be a pi bond, right? But this is a sigma bond. And that is basically the answer to this question. Now let's go to question 7. Explain the difference between cumulated, conjugated, and isolated multiple bonds. Name 3 compounds for each category. So going to lecture 18th, slide 5. We see the definitions. So double bonds are said, or multiple bonds in general, are said to be accumulated when they are right next to one another. For instance, if you have something like this, or if you have something like this. And in general, we talk about multiple bonds when we talk about like cumulated, conjugated, or non-conjugated. But specifically for cumulated, we cannot have triple bonds. Can you see why? Because if I have like 3 bonds here and double bonds here, in that case, they cannot be next to each other because carbon has like 5 bonds, which is not correct. So that's why for cumulated, we only have double bonds. Okay, so we call that cumulated. And if multiple bonds alternate with single bonds, they are called conjugated. So something like this. Or it can also be triple bonds here. These are also, as long as you have multiple bond, single bond, multiple bond. So that is conjugated. When more than one single bond comes between multiple bonds, the latter are isolated or non-conjugated. So if you have only one single bond between multiple bonds, this is conjugated. But if you have something like this, more than one single bond comes in between, or something like this. I'm just writing basically your book here. So this is non-conjugated or isolated. So remember the names because I'm going to ask you in your exam. Okay, and I said to write 3 examples for each. So that should be fairly straightforward. So let's do for cumulated. So if I just put hydrogen for each of these, what would this be? So here we have like 2 hydrogens here, right? And here we'll be having 2 hydrogen for this. So another compound can be for cumulated if I have for some reason this is not writing anymore. Okay, my pencil stopped working because it was out of battery, so it charged now. Okay, so first, if we want to work on cumulated, these are like 3 different structures that I can have, the most straightforward ones, right? Okay, so how would I write the name of this? Remember, we have, for the first one, we have 3 carbons, right? And we have double bonds. So the name should be, if we had only 1 double bond and we had 3 carbons, it would be propene, right? But So it will be propene. But we have more things, right? We have 2 double bonds. Remember that we would say diene, right? So it would be propadiene. And this is kind of weird to write it like this, right? So propadiene, right? So this is how we write the name. So let's practice one more. So we have like 3. Oh, so these 2 that I wrote here are basically the same. So let me have 5 carbons here. Or maybe I wanted these to be in order. So add 2 carbons here. Okay, like this. So if we want to write the name of this, we have 1, 2, 3, 4 carbons. So the name would be butane. So if we had only 4 carbons and we had 1 double bond, the name would be butane, right? But we have 4 double bonds. So it would be, or rather, sorry, we have like 3 double bonds. So it would be triene. So it would be butatriene. Okay, so we have like, again, since I was distracted before, we have 1 double bond, 2 double bond here, so we say diene. So we have 1 double bond, 2 double bond, 3 double bonds, we say triene, right? So let's work on the last one. We have 1, 2, 3, 4 double bonds. We have 1, 2, 3, 4, 5 carbons. So the name, if we had only 1 double bond, would be pentene, right? Tin. But we have, as we said, 4 double bonds. So we say tetra. And then tetra. This T here would be extra. So because it was pentene, it would be penta, right? Tetraene. So penta, tetraene. And again, these are like 3 examples. You can write any other examples that are basically represent cumulated. So let's work on some examples for conjugated. So I just write the book examples as a starting point. So it'd be 2 hydrogens here, right? 1 hydrogen here, 1 hydrogen here, 2 hydrogens here, right? The other conjugated can be like this. The second example of your book. So 1 hydrogen here, 2 hydrogens here. And remember, conjugated structures are when multiple bonds alternate with single bonds. Or I can have something like this, right? Right? And I put these hydrogens so that I have 4 bonds, right, between carbon and the other atom. So if I want to name the to write the name of these compounds. Let's do that. We name them so that 1, 2, 3, 4, right? If I go the other direction, doesn't matter, right? Okay, so we write the name of this compound as 1 and 3. We have 4 carbons, so it would be Bu something, right? So if it was like just one double bond, it would be butene, right? But we have 2 double bonds, so it would be diene. So it would be 1 and 3 butadiene, right? And I'm going to hold off to name of this compound because it has both double bond and triple bonds, and we didn't talk about them in the class. So I'm going to add another compound similar to the above one, but with more carbons. So it would be more straightforward in the sense of naming. So let's go talk about this one. So we say 1, 3, 5, right? We have 6 carbon, it would be hexa. If just only 1 double bond, it would be hexene, but we have 3 double bonds, so it would be triene. So it would be 1, 3, 5 hexatriene. What about this one? This is exactly the same. 3, 5, 6, 7, and I forgot these hydrogens here. So it would be again 1, 3, 5, but we have 7 carbons, so it would be heptatriene, right? Okay, finally, let's go to the isolated category. Oops. So isolated can be like this. You have like 2, more than 1 single bonds, right? In between double bonds or multiple bonds. So this can be an example. What about this one? Four carbons in between, right? What about this one? And this is the example of your book. And it would be 1 hydrogen here, 1 hydrogen here, 2 hydrogens here, 2 hydrogens here, and that's it. So let's name the first one. Okay, 1, it's not dependent, 1, 2, 3, 4, 5. So carbon number 1 and 4, we encounter the double bond. Let me change the color. 1 and 4. And we have 5 carbons. So if we had only 1 double bond, it would be pentene, but we have 2 double bonds. So we have 2 double bond in. So it would be 1 and 4 pentadiene. Here, same thing. 1, 2, 3, 4, 5, 6. 1 and 5. We have 6 carbons. It would be in main chain. It would be hexa. If we had only 1 double bond, it would be hexene. But here it would be hexadiene, and this di is 2. Here, 1, 2, 3, 4, 5, 6. Carbon number 1 and 5 is basically the same as above, but we have triple bonds. So it would be hexa, di, triple bond. This is a dine. And you're welcome to write any other example as long as you meet the criteria of the location of double bond, triple bond, and single bonds to be accumulated, conjugated, or non-conjugated, or isolated. And that was this question number 7, and 3 examples of each category. Let's go to question number 8. Draw the correct structure for 2 and 3 dimethyl 2-pentene. Okay, remember when we have like these two here, this shows the location of multiple bond. And here, because we have E and E, we know we have double bond. Since we have pentene, we know that we have 5 carbons in main chain. We have 2 methyl groups, and these methyl groups are on carbons number 2 and 3. So let's start with this, that we have 5 carbons in main chain. 1, 2, 3, 4, 5, right? And the second one, and I named them 1, 2, 3, 4, 5. The second one has a double bond. Remember that it should be here, because if it was here, it would be 1 pentene, okay? And the carbon number 2 and 3 has a methyl group on that, right? So let me have the rest of the hydrogens. CH3, 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4. Okay, so if I want to name this compound, I say 2 and 3 dimethyl 2-pentene. And that is the answer to this question. Okay. Number 9. What would be the major product of the following reaction? We have this cycloalkene plus HBr gives question mark. Okay. Remember that what we do in this type of questions, we eliminate the double bond and we add HBr to the two sides of the bond. So here, if I eliminate this and then I can add 1 Br here, or hydrogen here, or the other way around, right? Doesn't matter. And you can write the hydrogen here, or simply don't write it, because usually when we don't write hydrogen, it implies that we have like hydrogen attached to these carbons, right? So if we want to name this compound, how would we do that? So for now, I just stick with the first or second geometry that I draw here. So if I want to name this, remember from chapter 2, previous chapter, we would say, so we have like bromo and methyl groups, right? So we say 1 bromo, 1 methyl, and we have cyclopentane, right? So this is the answer to this question. Next question says, write the necessary reagents to convert 1 methyl cyclopentene to 1 methyl cyclopentanol. Remember that here you have like an alcohol, right? Pentanol. And here you have an alkene. So we should have OH, right? And do you remember what type of compound has OH? If you have like HOH, basically H2O, water, right? And we should have an acid in order to convert alkenes to alcohols. So we should have water and sulfuric acid. Okay, next question says, let me see which question are we. Okay, question, okay, this question, what would be the major product of the following reaction, right? Okay, so we are question 10. Okay, so question 11, and for question 10, I also had the structure, but that's why I was confused that I skipped the structure, but you can also work on this structure because I may give you that in the exam. But even without looking at the structure, just by looking at the names, you can know what is the answer to the question. Okay, what is the product for the reaction below? Plus HI. Okay, even not knowing the name of the reactants and products, you know the procedure based on what we talked in the class, that we drop the double bond and then add I to the both sides of the single bond now. So if we do that, we have like 1 I here and 1 hydrogen here. Again, we don't write the hydrogens because when you don't write the hydrogen, it implies that it's an hydrogen. So previously we had, and you remember to write carbons on each of these breaking points, right? Okay, so now if I want to write the name of this compound, what would that be? 2-iodo 2-methyl hexane. The reason being, you can start from here or here, 1, 2, 3, 4, 5, 6. So this would be your CH3 group methyl. This would be your iodo 2-methyl. And then since iodo is alphabetically prioritized, we write that first compared to methyl. Let's go to question 12. What is observed when water in the presence of sulfuric acid is added to 2-methylpentane? And we also have the formula here. So remember what we do in these instances. Oh, sorry, this is like the next question. Okay. That is the next question. So here, what is observed when water in the presence of sulfuric acid is added to 2-methyl-2-pentene? So we have 1, 2, 3, 4, 5, and 2-pentene. It means that 1, 2. In the second carbon, we have a double bond, right? And 2-methyl, CH3, right? 2, 3, 4, 5. So this is 2-methyl, 2-pentene. And we have like sulfuric acid as a catalyst, right? So remember that we break the double bond one, two, three, 4, 5, right? And then we add OH to one side and then H to the other side. So remember that we don't write the extra hydrogens, right? So we have like CH3 and have like this set CH3 1, 2, 3, 4. Then CH3, right? Or we can write the structure that we had here, 2, 3, 4, 5, and if we convert this double bond to single bond, we can add the, and we had like CH3 here, we can add the OH here and hydrogen here. So this can be another possibility. And then if we have like CH3, CH3, OH, CH2, CH2, and CH3. And as I said, I won't stress out about the name of the compounds that have OH, but you should know that they have like, they are alcohol, so they have like OL at the end of them. So in this case, we call this 2-methyl-2-pentanol. But I'm not going to ask them in the exam because we didn't talk about in much detail in the class. Now let me go through question 13. Okay, question 13 says, what is the product of the reaction? This. Plus HCl gives. So what we do is that, as we talked about in the class, we eliminate the double bond and just with the double bond that we converted to single bond, for each carbon, instead of the double bond, we add hydrogen and Cl. So if we do that, we can write this like in better format as like this, CCl, and then we have CH2, CH2, CH3, right? And then here we can have CH3, 2. So this would be the product of that reaction. And since I didn't ask the name, you don't have to write the name. But if I ask you the name in the exam, you should be able to write the name. Okay, let's go to the next question, which is question 14. What is the product of the reaction CH3, CH2, C, triple bond, CH plus 2, Br2? Okay, remember that now we have like 4 Br atoms, and we eliminate these 4, basically these 2 double bonds here. So if we do that, we add 4 Br atoms here, right? And we can also write this as CH3, CH2, C, Br2, CH, Br2. Okay, let's go to question number 15. Okay, in the chlorination of methane, the propagation steps involve forming what species? Okay, this is lecture 13, February 11, 2022. And when we talked about halogenation of alkanes, remember that we had initiation, we had propagation, and we had termination, right? In initiation step, we had the halogen molecule being broken down to its atoms. So we had, like, for instance, chlorine atoms or like bromine atoms, depending on what we had. In the propagation step, we had like RH or alkane plus one of the atoms of the previous step, right? Or like one of the halogen atoms giving alkyl radical plus HCl or HBr, depending on what we had, right? And also we had like the radical plus one of the halogen molecules giving RCl plus the other halogen atom, one halogen atom. So basically RCl plus the Cl itself, right? And in the termination step, all the radicals came together. So whether like Cl plus Cl gives Cl2, or R plus R gives R2, or R plus Cl gives RCl, right? So now that we know this, in the chlorination of methane, the propagation steps, so we say steps because there are 2 steps, right, involve forming what? So we have alkyl radicals, and we also have chlorine radicals, right? And we also have, HCl and we also have RCl. So here, because we have like methane, we would be having methyl, be having hydrochloric acid, we would be having chlorine atom, and we would be having methyl chloride. Okay, now question 16. How many monobromo products can be obtained from the bromination of cyclopentane? And we solve really similar question, if not the same, in the class. So remember cyclopentane, right? And we said we have like carbons on each side, CH2, right? Because we have 2 bonds here already. We have 2 hydrogens, CH2, 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 CH2. So since we are asked about monobromo products, it means that if I substitute 1 Br here, if I substitute it here, right, or like with one of these hydrogens here, or one here, or one here, right, or here, all of them are the same. So it would be only one monobromo products, right? And we talked about that in the class. And you can refer to the corresponding lecture. I can also find out which lecture specifically it was. I believe it should be lecture 14th, but I can find that out real quick. Or 15th. Okay, lecture 17th. And it was exactly, we talked about cyclohexane. Slide. Yeah. For instance, slide 24. It's really similar. Different problem, but really similar concept. Okay, let's go through question number 17th. What is the number of electrons in the valence shell of sulfur? Okay, sulfur belongs to group 6A, so it has 6 valence electrons. That was an easy one. Okay, question 18. Which of the following molecules are structural isomers? To see structural isomers, first write the formulas of each of these. And CH3, CHOH, CH3, CH3CO, CH3. So this would be C3H8O. This would be C3H8O. This C3H8O. This would be C3H6O. So we can see that these 3 are structural isomers because they have the same molecular formula but different structures. Okay, let's go to the next question, 19. What is the molecular formula for this compound? Okay, so this is easier than questions that we saw before. We just add carbons on each point that you see here, right? And then you count the hydrogens. Here it should be 2. You have 1, 2, 3, 4. This is all set. 1, 2, 3, 1 hydrogen. 1, 2, 3, 4. We want to have 4 bonds. So 2 hydrogens here, 2 hydrogens here, 1 hydrogen here. So it would see 1, 2, 3, 4, 5, 6, 7. Then H. 2, 4, 6, 8, 10. So the molecular formula would be C7H8. And finally, the last question, which of the following structural formulas has the molecular formula C6H12? What we do is that for each of them, we write the molecular formula. So it would be 2 here, 2 here, 2, 2, 2, 2. It would be 1, 2, 3, 4, 5, 6. Be 1, 2, 3, 4, 5, 6. Okay, what about this one? So 1, 2, 2, 2, 2, 1. Right, C6H10. What about this one? H3, H, 1, 2, 3, 4. 1, 2, 3, 4. 3. 6, H, 10. Right. Let's go to the next one. What about this one? H3, H, H2, 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 H2. 4. Right. Okay, and the next one. C would be 2 here, 2 here, 2 here, 1 here, 2 here, 3 here. Right. So you see this structure, and this structure, they have C6H12, which in the figure are like 1, 4, 5. Right. Okay. So I hope this video has been useful for you all, and just contact me if you have any questions. And hopefully I can upload this before I go to bed tonight. Okay, everyone, have a good morning. Probably you'll see this tomorrow if you start working on this on Friday. But I really wanted to post this sooner than later, so that's why I started recording today instead of tomorrow. So hopefully it will be useful. Just reach out to me anytime if you have any questions.